Gyroscopic instruments. Gyroscopic instruments allow flight to take place without a visible horizon, making it possible for planes to fly in bad weather or at night. A typical airplane uses about a dozen gyroscopes in everything from its compass to its autopilot. Gyroscopes resist turning. When they're gimbaled, which means free to move in any given direction, gyroscopes will remain in the same orientation in space while their housing moves around them. Before we take a look at their use in aircraft, we'll explain the basic principles of a gyroscope: rigidity in space and precession. Rigidity in space. What makes gyroscopes useful is their fundamental property of rigidity in space. What rigidity in space means is that gyroscopes stay in a fixed position in the plane in which they are spinning. Think of a bicycle. The faster the wheels of the bike are turning, the harder it is to turn the handlebars. The slower the bike wheel turns, the less stable and thus easier to turn it is. This is also why you can't flip a fidget spinner. Trust us, we've tried. Gyroscopes seem to drift away from their original axis over time. However, this is not because they are moving. They are in fact staying in their plane while the Earth moves around them. If you stood at the equator with a freely mounted gyroscope, you would observe it making a 360-degree turn over a period of 24 hours. Precession. When a force is applied to a gyroscope's axis, it doesn't behave as you would expect it to. It results in a tilt of the axis, 90 degrees in the gyro's direction of rotation from the point where the force was applied. To explain this, think of a ball moving in a straight line. If a force is applied to it, its path changes from when it was applied onwards. If the ball is travelling in orbit, the same logic applies. When a force is applied to it, its original momentum and the applied force sum up to give the new path of the ball. This results in the axis of rotation being tilted. Continuing on with the orbit idea, think of the ball as a point on the gyro's orbit. When a force is applied to a point on the gyroscope, the axis tilts in the direction of the force, not where it was applied, but 90 degrees in the direction of rotation from the point where it was applied. This principle is known as precession and has to be corrected for in all gyroscopic instruments, where it can be caused by both friction within the gyro and by the aircraft turning, accelerating and decelerating. The gyroscopic instruments. The gyroscopic instruments provide the pilot with the pitch, bank, yaw and heading of the aircraft at a glance. They are the turn coordinator, which used to be the turn and slip indicator, which shows both roll and yaw. The heading indicator, which shows the plane's heading with respect to magnetic north. And the attitude indicator, which shows pitch and bank information simultaneously. Let's have a closer look at the attitude indicator. An attitude indicator consists of a miniature plane, an artificial horizon, and the bank index. The miniature airplane, consisting of two horizontal lines with a dot in the middle, stays still, while the artificial horizon moves around it. But how does it work? The gyroscope keeps the artificial horizon parallel to the Earth's horizon, with the whole aircraft in effect moving around it. Earlier on we mentioned precession, and the fact that it needs to be corrected for. The attitude indicator is no exception. Vacuum-powered gyroscopes correct precession with pendulous vanes. These can be described as pendulums covering vents which swing open when the gyro is no longer pointing straight down towards Earth. Air then blows through the vents, correcting the gyroscope's position in relation to the surface of the Earth, and the pendulous vanes swing shut again. If the pilot pitches or banks too hard, the gyro may tumble, which is why many attitude indicators come with a caging or erecting mechanism to return them to an upright position.